So I said in the previous lesson, what we're going to start to do is look at applications for centripetal force, and that the first application that we look at is the circular orbit due to gravity. So let's look at this application and try to figure out what's going on in this particular situation or system. So here I have a satellite that's in orbit around, it looks like the Earth, and that arrow points almost like right to Kansas or something like that. But the cool thing to point out about objects that are in orbit around the Earth is that they're in orbit because of gravitational attraction with the Earth. They're technically falling toward the Earth. They would be in what we call free fall. If you might think back to Unit 2 on kinematics when we talked about free fall, remember how we defined free fall, that it is an object that is falling toward the Earth under the influence of gravity. An object in a circular orbit is exactly that. The only force that's acting on that object is gravity. Now you might ask yourself, well then how does it move around the Earth? What's really happening to this system? Well, remember that it could have horizontal velocity like a projectile. If we think about projectile motion, well, if you get the horizontal velocity fast enough, you can fall in a circle around the Earth. If you're falling at the same rate that the Earth really curves underneath of you, guess what? You're in orbit around the Earth. This, of course, makes the assumption that you believe that Earth's a sphere and not flat, but, well, there's plenty of evidence floating above our heads that you can go out on a really clear night and look up and see. If you've ever looked up in a place where there's not a lot of light pollution, it's really hard to do on campus, but if you only go a few miles out of town, you can actually look up and see satellites in orbit around the Earth. And it's actually really easy to see, and it doesn't take very long because there's just so many of them in orbit. So gravity is the thing that's responsible for holding things in orbit. So let's look at how we begin to model this system. And how we talk about gravity when we're not talking about things that are close to the Earth. Well, calculating the force due to gravity of like something being dropped from the clock tower is pretty easy. It's mass times g, 9.8. But when we start to talk about things that are further away from the Earth, where the acceleration of gravity may not be 9.8, we have to have another way to describe that. And we've actually already done that. If you go back to the unit on forces, we talked about Newton's law of gravity as a more general way to describe the gravitational attraction between two objects. And the way this formula works is to do g, the universal constant of gravity, times the mass of the satellite, which I'm going to call little m in this case, times the mass of the planet, in this case Earth, I'm going to call the big M, divided by r squared. Now it's worth pointing out r is not the distance you are away from the surface of the Earth. R is really the distance you are away from the center of the Earth. The orbital radius and the orbital height are two different things. The orbital height would tell you how far you are away from the surface of the Earth. The orbital radius will tell you how far are you away from the center of the Earth. Now, if we set that equation equal to mv squared over r, centripetal force, we can do a couple of quick things to solve this for v very quickly. The first thing that happens is the mass of the satellite cancels out. The second thing that happens is one of the radiuses cancel out. If I multiply both sides by radius, I get r on the bottom of the left-hand side. So I get v squared is equal to gm over r. And so if I square root, really what this says is the orbital speed, the speed necessary to be in a circular orbit, is really equal to the square root of the universal constant of gravity, that 6.67 times 10 to the negative 11th, times the mass of the object you're orbiting around, divided by your orbital radius. How far are you away from the center of that object? This also works really well to predict something like the orbital speed of a planet around the sun. Put the mass of the planet in there, put the orbital radius in for r, and you can get the speed of those planets. What this would say about satellites orbiting around the Earth is that the only thing that determines the speed that satellite's in is your radius of your orbit. How far are you away from the center of the Earth? That probably isn't all that shocking because as you get further and further away, you get larger and larger circles. It takes less speed to fall around the surface of the Earth. And in fact, the force of gravity gets less and less and less the further away you get. And so you fall at a smaller rate to begin with. It's actually, in some ways, this problem that Isaac Newton was really starting to think about when he thought about his universal law of gravity. He was starting to think about it in terms of projectile motion. If you launch a projectile fast enough, it would be theoretically possible that if it falls at the same rate that the Earth curves underneath of you, that you could move in a circle around the Earth. So Isaac Newton really is starting to think about these circular orbits when he's starting to think about the Newton's law of gravity. He doesn't really know that it's possible to put something in orbit in space around the Earth. That'd be a complete fantasy to him at that point. So let's do an example problem. And the example problem I picked is the Hubble Space Telescope, which is a telescope that was launched in the late 80s, early 90s, and has really been in space since then. There was a repair mission to repair a lens, or no, excuse me, a mirror in it. One of the things that happened in the manufacturing process of this telescope is one of the mirrors was not correctly manufactured, and so the images always came back a little bit blurry. They managed to manipulate the computer program that processes the images on the Hubble Space Telescope to correct some of that blurriness, but it really wasn't possible to do all of that. In the mid-90s, a mission was undergone to replace that mirror. So you can imagine we put this fancy, probably thousands upon probably hundreds of thousands of dollars mirror onto a space shuttle and launch it into space, and then we're going to replace the mirror in really a spacewalk. Really crazy procedure, but it worked, and the Hubble Space Telescope still is used to capture images of things far away and is still being used for research of distant objects. It actually captures really, really good pictures now. The reason to put this telescope up there is that if it's outside the atmosphere of the Earth, you capture pictures that don't have atmospheric distortion in it. As light enters the Earth's atmosphere, it gets distorted, and so even on a really clear night, you still get images that are distorted if you take a picture with the best telescope on Earth. Even if you put it on top of Mount Everest and have the clearest night you can possibly have, you would still have fuzzy images due to atmospheric distortion. In the Hubble Space Telescope, you don't get that anymore. Well, the orbit of Hubble Space Telescope is 598 kilometers above the Earth's surface. The other crazy thing about this mission is this is one of the furthest missions that the space shuttle ever took from the Earth's surface. So the first thing we need to do is, well, we need to know the mass of the Earth, the universal constant of gravity, and the radius, if we want to calculate the radius or the speed of this orbit. Pretty easy to find the mass of the Earth, 5.98 times 10 to the 24th kilograms. The universal constant of gravity, 6.67 times 10 to the negative 11th. And so now we need to find the orbital radius. Well, remember, that is not the 598 kilometers I put in there because that's the orbital height. So we want to do the orbital height plus the radius of the Earth. So I went and looked up the radius of the Earth, and that's 6.38 times 10 to the 6th meters. So if we were to look at this orbit, if we looked at the Earth as a circle and then the orbit the Hubble Space Telescope's at, it's really like just a little bit above that circle, not very far, because the orbital radius is 6.98 times 10 to the 6th meters. It's not very far above the surface of the Earth compared to the radius of the Earth, which may seem crazy, but that's the reality. In fact, the vast majority of the things we have in space are like, if you think about the Earth as an onion, and then think about like one extra layer on the onion, the vast majority of things that we have in orbit are in that one extra layer of the onion. That it's really that size or that distance away from things. Well, once we know all of that stuff, we can just plug it into our equation and calculate. I would say one of the biggest challenges to doing this equation is you get numbers in scientific notation. Remember, particularly when you're dividing by a number in scientific notation, that you either want to use the function on your calculator where that puts numbers in scientific notation, or you want to be very careful to put it in parentheses. Otherwise, you're going to get numbers which don't make any sense. And we find for the orbital speed is that it's 7,560 meters per second. You could probably Google this if you want and just see if I've done my calculation correct. I'm pretty sure the orbital speed of the Hubble Space Telescope is something you could figure out on Google pretty quickly. I would challenge you to do that and just double check my math. Now, the second thing we could do is we could find the height above the Earth or the orbital radius for a satellite by knowing its orbital speed, or maybe its orbital period, since period and speed relate to one another. Here I want to figure out the height above the Earth of a geosynchronous satellite. So you might ask, what do we mean by geosynchronous? And what geosynchronous means is that it stays above the same location on Earth all the time. What that means is its orbital period and the rotational period of the Earth are the same thing, 1 day. So it means its orbital period around the Earth is a single day. Now you might ask, why would we want to do this? But it happens to work out there are lots of applications of geosynchronous satellites. Communication satellites, for example, many of them are geosynchronous. If you have satellite television, you are getting your signal from a geosynchronous satellite. How do you know? Well, you don't have to go outside every 15 minutes and wiggle your satellite dish until you get your satellite signal back. The satellite dish on your house points one direction all the time, and the signal you get is a clear signal all the time. Well, unless it's like super cloudy or there's something else wrong with your satellite dish. That would tell you that the satellite that is giving you that signal is over the same location of Earth at all times. I would also tell you satellites that give you satellite TV, the majority of them are over the Earth's equator. And so here in the northern hemisphere, pretty much everybody that has satellite TV has a satellite dish that points to the south. And in the south, probably about at an angle that's equal to what we say 90 minus your latitude. Above the horizon. So here in Minnesota, they're probably pointed about 45 degrees above the horizon because that's going to give you something that's about orbiting over the equator. You could do the geometry of this and prove that's true. I'm going to tell you that it's true. So other applications of this, communication satellite's a great application. Another application might be maybe a little more clandestine. If you are a country and you have a particular interest in watching another country all the time to see what they're doing, you might put in a satellite in a geosynchronous orbit. We'll see that there's a disadvantage to that when we calculate the height above the Earth, and the disadvantage to that is you got to put it pretty high above the Earth. So you trade off your ability to take really good pictures by being able to watch what's happening over that country at all times. So there's a trade-off in there, and we'll figure out why that is when we calculate the height above the Earth. So if we wanted to calculate the orbital speed, we could calculate r, the orbital radius, from the orbital speed. I know the orbital speed relates to the period in the radius. And I know what the period is, 1 day, or 86,400 seconds, give or take a few seconds. It's worth pointing out that the day is not exactly 24 hours. It is, I believe, a hair less than 24 hours. And I think it's like milliseconds less than 24 hours. We'd go look that up if we wanted to, but for our purposes, a 24-hour day works perfectly fine. So what I'm going to do is I'm going to put in what the equation for speed is in terms of period, because I know the period. And what I end up with is an equation where really the only thing I don't know is radius. The problem is I have radius on both sides of the equations. And on one side of the equation, it's underneath a radical. So that makes it even, harder. The first thing I'm going to do is square everything to get rid of that radical so that I can maybe potentially get rid of that radius on the bottom of that equation. And by squaring everything, I get 4 pi squared r squared over period squared on the left-hand side, and I get gm over r on the right-hand side. I can now do a little bit of algebra and get everything on, or all the r's on one side and everything else on the other side. What I'm going to do is multiply by period squared, divide by 4 pi squared, and multiply by r on both sides. And so what I'm left with is r cubed is equal to g times m times period squared over 4 pi squared. So what's worth pointing out here is that the period of your orbit is also related to the radius of the orbit. If you're in a circular orbit, and it's related by this weird equation. Now this weird equation actually shows up somewhere else in physics as well. When we talk about orbital mechanics and planetary orbits, a guy by the name of Johannes Kepler, actually before Isaac Newton, so he doesn't know Newton's law of gravity exists, came up with an equation that looks really kind of similar to this. He said the period of planetary orbit squared is related to the distance the planet is away from the sun cubed. And that actually works out really, really well for the planetary orbits. Uh, so this guy Johannes Kepler is really coming up with this exact same relationship through a different way. How he came up with it was he used a bunch of observational data about the motion of planets in the sky and kind of interpreted how far they have to be away from the sun and what their periods have to be by what their orbit or what their motion in the sky look like. Completely crazy how you could come up with that, but he came up with that in an era without computers, without calculators, without cell phones. I don't even think he had the slide rule at that point. All pencil and paper, math and geometry. It must have taken him years. But he came up with this relationship. We could actually rearrange this a little bit and say that the radius of my orbit is equal to the cube root of g times m times period squared over 4 pi squared. And if I plug in all my numbers, I get the radius of my orbit is 4.23 times 10 to the 7th meters. Now remember what the question asked before was, what is the height above the Earth? And that this is not the orbital height, but the orbital radius. This is talking about the distance from the center of the Earth. So what I need to do is subtract the radius of the Earth, and so I get the height above the Earth is 3.59 times 10 to the 7th meters. Now if you're interested, you could divide that by 1,000. 3.59 times 10 to the 4th kilometers. That's like 36,000 kilometers above the surface of the Earth. That's really far. So you can see what the disadvantage to doing this if you're going to try to say, look at what another country is doing all the time. You're probably not taking pictures at this point. You're probably doing something else or some other way of listening into what's happening in another country. Maybe listening to radio or trying to pick up TV signals or something like that that you might be able to pick up from a satellite. Though even radio signals at this distance are going to be really, really difficult to detect. But there may be other things you might be wanting to do. So these satellites that you're getting your satellite television from, they're like really far away from the Earth, especially compared to the Hubble Space Telescope, which is hundreds of kilometers away from the Earth. These things are 35,000 kilometers away from the Earth. That's a really far distance. So that's a couple quick examples of circular orbits and how they actually work out, and a couple of equations that we can use to describe the circular orbit.